Hello, grade 10 students. In this video, we're going to talk about the nervous system, part 3. So this graph represents the membrane potential or the action potential in nerve fiber with the different phases, phase 1, 2, 3, 4, 5, 6, and 7. These are the different phases of an action potential where 1 represents the resting potential where no stimulus is applied. Number 2 represent the artifact, which is called the hypopolarization. We said that polarization is negativity, hypo decrease. So hypopolarization, it's decrease in the negativity. Phase number 3 represents the depolarization. We're going to move to the positive. And number 4, which is this region number 4, it represents the inversion of polarity, moving from the positive down to the negative. And then we have phase number 5, repolarization, where negativity is retained back. Phase 6 represent the hyperpolarization. Hyper means that high, like we say hyper active. So hyperpolarization, it's increase in the polarity, meaning that increase in the negativity. And phase number 7, which is returning back to the resting potential. So as a revision, this represent the phases of an action potential, where phase number 1 represent the resting potential minus 70 millivolt where no stimulus is applied. Phase 2, it represents the hypopolarization, decrease in the negativity, as well it's called artifact. Phase number 3 represent moving to the positivity, depolarization, moving from minus 70 to about plus 50. It's called depolarization. Number 4, it's the inversion of polarity, moving from the positive toward the negative. And phase 5, it represents the repolarization, going back to the negative. Phase 6, hyperpolarization, increase in the negativity. And phase number 7, it represents the returning to the resting state. So these are the different phases. As I said, number 1 is the resting potential where no stimulus is applied, where number 2 it's hypopolarization, which is called the artifact. Number 3, depolarization. Number 4, the inversion of polarity. Number 5, repolarization, going back to the negative. Number 6, hyperpolarization, increase in the negativity in a higher value than the one recorded in the resting potential, which is minus 70. And number 7, it's returning back to the resting state. Let's now talk about the phases of the action potential at the level of the electric understanding. So depolarization. As we said, depolarization, we're going to move to the positive. It corresponds to the hypopolarization. Hypo, it's less. Polarization, negativity, as we said before. So hypopolarization, it's decreased in the negativity. It was minus 70, it moves to the about 120, it moved to the 50. So minus 70 plus 50, it's 120 millivolt. This means that the interior becomes more positively charged with respect to the exterior, which become more negatively. That's why we have depolarization. Now let's move to the repolarization. Repolarization is going back to the negative. It corresponds to the return back to the initial state, where the potential difference decreases or it drops from 50 to minus 70 millivolt. This is the phase number 5 in the graph of the phases of the action potential. So this means that the nerve fiber is negatively charged interior, it's more negatively charged in the interior with respect to the exterior, which becomes more positively charged. Now we're going to talk about the hyperpolarization. Hyper meaning increase, polarization, increase in the negativity. So this corresponds to the increase in the electronegativity of the interior. of the nerve fiber, where delta V drops or decreases to less than minus 75 millivolt approximately. So this means that the interior is now more electronegative compared to the resting state, which is about minus 70 millivolt. We're going to talk about the ionic charges. First, we talk about the understanding about the electric understanding at the level of depolarization phase number 3, repolarization phase number 5, and the hyperpolarization, which is phase number 6. Now we're going to talk about the ionic changes, the differences at the level of the ions. First of all, let's start with the resting phase, resting state. It corresponds to the delta V is equal to minus 70 millivolt. So in this state, the cell membrane is highly permeable to K plus. So more K plus on the inside and more Na plus will be on the outside. This happens in the resting phase. So you have to know that more K plus will be on the inside and more Na plus will be on the outside. Why? Because the membrane is highly permeable to K plus than that of the Na plus. Number 3, the depolarization. Depolarization meaning now moving toward the positive. So the membrane permeability to Na plus will increase. So more Na plus channels will open. So more gates for Na to enter. And the permeability to the K plus decreases. K channels or K gates, potassium gates, will close. So more positive charges will accumulate on the interior of the fiber. As such, it becomes more electropositive. So here, depolarization, repeated, the membrane to permeability to Na plus will increase and more Na plus channels will open and permeability to K plus will decrease, K plus channels will close. So more positive charges accumulate on the interior of the fiber. As such, it becomes more electropositive. Okay, this is the depolarization phase. Let's move now to the repolarization phase. Repolarization phase, as I said, the membrane permeability to Na plus decreases. So the Na plus channels, what will happen for them? They will close and permeability to K plus will increase. As such, K plus channels will open. So more positive charges accumulate on the outside of the nerve fiber. So the interior becomes more electronegative. That's why we move back to the polarity in the phase. You have to know that sodium ion channels, they close, and depolarization triggers the opening of voltage gated potassium ion channels, and then the K plus will rush out of the cell, repolarizing and then hyperpolarizing membrane. You have to know that the hyper increase, polarization, negativity. So the increase in the negativity, the K plus channels, they are still open. So they are too slow to close. So more positive charges will accumulate on the outside of the fiber as compared to the resting one. So the interior becomes more electronegative, even more electronegative than the resting state, which is minus 70 millivolt. Okay, so hyperpolarization, the K plus channels, they are still closed, still open, sorry, they are too slow to close. So more positive charge accumulate on the outside of the fiber as compared to the resting. So the interior becomes more electronegative, and even it's more electronegative than the one in the resting state. So in the hyperpolarization, since the K channels are still open, so more positive charges will accumulate on the outside, so more electronegative will be the interior of the nerve fiber, and that's why the negativity will be more than that in the case of the resting state. So this is the interpretation at the level of the ions for the hyperpolarization. Okay, let's move now talk about the resting potential, how it's resumed. Resuming the action potential, the potassium channels they will close, and repolarization will reset sodium ion channels. The ion diffuses away from the area, and the sodium potassium transporters maintain polarization. These notes you don't have to study them, just for general information. Okay? So sodium potassium transporters they maintains polarization, and the membrane is now ready to fire again and to start again in action potential. These figures represent the returning to the resting state polarization. Then the Na plus channels they open and the K plus channels they are closed in step number 2. Threshold potential is reached and action potential is triggered. Phase number 3, Na plus channels they close and inactivate while the K plus channels they open and K plus brushes outside. And phase number 4, K plus channels closes relatively slow, causing in a brief undershot, and they go back to the hyperpolarization, and then we go back to returning to the resting state. You have to know that the law of the the nerve fiber obeys the law of all or none. What the meaning of this? And pay attention to this note. This is a very important note. If we have a weak stimulus, it's below the threshold value needed to trigger an impulse. So there is no action potential. So this shows that whenever we have a response or a stimulus which is weak, below the threshold value, below the value needed to trigger an action potential, so there is no action potential. While we have a stimulus just above the threshold, so this value is above the threshold, so this one is said to be effective one. So this will cause depolarization of the membrane, and then we have an action potential. So this one is called the threshold of excitation. It's the first one to cause an action potential, while the weak stimulus is said to be the ineffective stimulation. Why? Because it doesn't cause the appearance of the action potential. So pay attention to this and be careful that the weak stimulus that doesn't cause the appearance of an action potential. It's called the ineffective stimulation. It doesn't cause the appearance of the action potential. While the first stimulus to cause the appearance of the action potential is said to be the threshold of excitation, whereas the strongest stimulus they are said to be effective stimulation. Let's see here. We start threshold 1 and a stronger stimulus. If you see here, all of them they have the same frequency as the one here. So first of all, you have to know that the nerve fiber obeys the law of all or none. Either we have an action potential or not. This is first. Second, frequency, it's approximately the same frequency. No, it's the same amplitude. So amplitude meaning that the value is the same value, but it differs in the frequency. Okay, how many times it repeats itself. So you have to know that the amplitude is approximately constant, while the one that differs is the frequency. So when the nerve zone of a nerve fiber is excited efficiently, depolarization occurs and an action potential is created. This depolarization stimulates the depolarization of the neighboring zone ahead. This is because the previous zone is said to be a refracted period, or it's not excitable. As such, the message propagates forward and never backward, so it moves in only unidirectional manner. So you have to know this important note that the nervous message propagates in a unidirectional manner, meaning that from dendrite to the cell body to the axon to the next cell, dendrite, cell body, axon, and to the next cell, and so on. And it never moves backward, so it moves in a unidirectional manner. So pay attention to this nervous message. It moves or it propagates in a unidirectional manner. the saltatory conduction, the jumping of an impulse between the nodes of Ranvier in a myelinated axon. So this will dramatically increase the speed. So it only occurs in axon having myelin. It increases the speed from 2 meter per second to about 120 meter per second. So it's about 60 times higher or faster. Factors that affect the speed of propagation of the message in a nerve fiber. We said we have the diameter, we said we have the myelination, and we have temperature. T1, T2, nerve fiber 1 temperature is T1 20 degrees Celsius, and in nerve fiber 2 it's T equal 30 degrees Celsius. So the T1 it's less than 2, so the V1 will be less than V2. So we can conclude here that the as the temperature of the nerve fiber increases, the speed of propagation of the nervous message will increase as well. Factors that affect the speed of propagation of a nervous message in a nerve fiber, we have drugs. Drugs, they are divided into two types, either stimulants or tranquilizers. Stimulants, they accelerate the nervous message, like for example the coffee. Some of you, for example, your mom, your dad, they said didn't wake up exactly or 100% unless to drink coffee. So coffee, it contains caffeine. So this is a type of stimulants that accelerate the nervous message, meaning that it make it faster. While tranquilizers, they decelerate the nervous message. They make it slower. It's like sleeping pills, for example. Okay. So here we have the figure. We are going to talk here in specific about the dorsal root and about the ventral root. Dorsal root containing the efferent, ventral, efferent. So efferent it's motor, afferent it's sensory. The pathway of the nervous message through a spinal nerve. We have this experiment. This experiment is a very important experiment in grade 10 biology and in the nervous system. This is one of the most important experiments. Excitation of the ventral root of a spinal nerve. What will happen? Excitation of the dorsal root, excitation of the central end, excitation of the peripheral end after the sectioning of the ventral root, and so on. So, excitation of the ventral root of the spinal nerve, we have contraction, while excitation of the dorsal root, we have contraction with the feeling of pain. So, let's interpret these results. First, after excitation of the ventral root of the spinal nerve, we have the concerned part contracts. This indicates that the nervous message propagates from the ventral root toward the muscle, which is the concerned part. So this one, it has a motor function. While after we did the excitation of the dorsal root of the spinal nerve, we have contraction with a feeling of pain. So this indicates that the nervous message propagates from the dorsal root toward the spinal cord, and from spinal cord to the brain, and then to the concerned part. So it moves from the spinal cord to the brain and then to the part. So it has an efferent way. So it has a sensory function. So till now we deduce that the ventral root, it has a motor function, whereas the dorsal root, it has a sensory. Motor, since we have contraction of the concerned part, so the nervous message was propagated from the ventral toward the muscle, so it has a motor function, whereas the dorsal root, after its excitation, it contracts and the animal feels pain. So this indicates that the nervous message was propagated from the dorsal root to the spinal cord, and then from the spinal cord toward the brain, and then toward the concerned part. So the dorsal has a sensory function. Experiment 3, what did it do? After the sectioning of the ventral root and exciting the central end, there is no reaction. So here we can deduce that the nervous message stopped at this section. It doesn't move. While excitation of the peripheral end After the sectioning of the ventral root, the muscle contract. So here, the nervous message moves toward the muscle. So it propagates in a centrifugal manner in the motor. It's away from the center. Whereas after the sectioning of the dorsal root and excitation of the central end, we have contraction and the feeling of pain. So this means that the nervous message propagated to the spinal cord and then to the brain and then to the concerned organ or muscle. So after the sectioning of the peripheral end, after the sectioning of the dorsal root and excitation of the peripheral end, there is no reaction. So the message stopped at this section. So in the dorsal root, the nervous message propagates in a centripetal toward the central nervous system, brain and spinal cord and brain, and then to the muscle or the effector organ. So you have to know that the nervous message propagates in a centripetal direction or manner in the sensory dorsal root, while it moves in a centrifugal manner in the motor ventral root. While the last experiment, after destruction of the spinal nerve, there is no reaction, and we have total loss of motor activity and sensation. So this means that the spinal nerve has both function. It has motor and sensory. So this is the interpretation. So after excitation of the ventral root of the spinal cord, the concerned part contracted. So this indicates that the nervous message was propagated from the ventral toward the concerned part, which is the muscle. So the ventral has a motor function. This is the first one. Second experiment. After excitation of the dorsal root of the spinal cord, the concerned part contracts and the animal feels pain. This indicates that the nervous message was propagated from the dorsal root toward the spinal cord, from it to the brain, and then to the muscle. Therefore, dorsal root, it has a sensory function. So dorsal, sensory, ventral, it has a motor. Then, third experiment, after sectioning of the ventral root and excitation of the central end, there is no reaction. So the nervous message was stopped at this section. Whereas, after sectioning the ventral root and exciting the peripheral end, the muscle contracted. So the nervous message propagated toward the muscle. This indicates that the nervous message propagates in a centrifugal manner in the motor ventral root. So you have to know that the nervous message propagates in the centrifugal manner in the motor ventral root. By the way, these highlighted one, you can study them, okay? Because this experiment is constant and you can study these highlighted one as conclusions. For example, you have to know that in the nervous message in the motor ventral root, it propagates in a centrifugal manner. Fourth experiment, after sectioning the dorsal root and exciting the central end, contraction occurred and a feeling of pain was recorded. This indicates that the nervous message propagated to the spinal cord, to the brain, and then to the muscle, while after sectioning the dorsal root and exciting the peripheral end, no reaction occurred. This indicates that the message was stopped at this region or at this section. So therefore, the nervous message propagates in a centripetal manner, meaning that toward the center, toward the brain and the spinal cord, or the spinal cord and the brain. The last experiment, after destruction of the spinal nerve, there was no reaction and total loss of sensation and feeling of pain and the motor activity. So this indicates that the spinal cord has a mixed function, motor and sensory. Okay?